Let's talk now about force oscillations. Okay, so in the context of force oscillations, this is one of those moments where I would say the force is with you. Okay, and saying that the force is with you, with us, means that here in this diagram we have a mass body of, or an object of mass m that that has the force with it. Means the force is pulling that mass towards some direction there, right? So these diagrams should be in your mind associated with the equations of motion that we describe here, where x as a function of time denotes distance, and then we have in this equation the rate of change of distance and the rate of change of the rate of change of distance, right? And so we write the mass m as a coefficient of the second derivative. That's what appears here. And then we also have coefficient c, which denotes damping, right? You could also consider that coefficient the action of friction. Okay, as I was saying, this m is a parameter or constant that denotes the mass of the object. And we also have this other parameter k, which is a constant that denotes, it's called the spring constant. So either you write equations first and then draw that picture second, or you draw the picture first and then derive the equations next. But a very important thing is that this is equated to an expression here that is considered capital F, a function of t. So let's now consider a scenario that we name undamped force motion. So that would be, so let the friction or damping be set to be identically 0, and then we would write using the prime notation, we would write this as x double prime plus 0 times x prime plus kx equals to f of t. That's the so-called force. In other words, here we would write something like m x double prime plus kx equals f of t. Now we're going to make an assumption. We're going to say, hey, suppose we're going to set we're going to assume there's a specific form for this forcing. So we're going to say, suppose f of t is of the form a constant f sub 0 cosine of omega t. Let's suppose that that is the so-called forcing, and so that would imply, this would imply that this second order equation would look like m x double prime plus k times x equal to f sub 0 f naught cosine of omega t. So we need to find a solution for this. Right, this is now what we would like to devote efforts. And so what we want to do is find a solution. That's what we want, find a solution of that. So first, let's consider a complementary solution. So we're going to write, denote this as x sub c, right? This is x sub c of t. And we're going to propose that this has the form c1 cos plus c2 sine, where the arguments of these trigonometric functions are going to be given by omega 0 of t, omega 0 of t. Those are the arguments there in the proposed complementary solution. And more specifically, we're going to elaborate here. We're going to say, look, this omega naught or omega 0 is going to be given by the square root of the ratio k over m, right? K, the spring constant, divided by the mass of the object. And this is going to be considered the natural frequency of this mass spring system. Okay, this mass spring system. So in the sense that the system, natural frequency, in the sense that this spring system wants, as if it has a will of its own, this spring system wants to oscillate with external forces. Okay, so that's the meaning of this omega 0 or omega naught, this constant. Now, we have some experience with this type of equation, right? So let's remember that this equation here is an equation of second order, and when we are solving for the proposed complementary solution, then we're really considering, we're going to say, remember, we're really considering the problem mx double prime plus kx equals 0, right? So we're going after a solution to this equation, and so here we're going to do the following. We're going to make the coefficient of the highest order derivative, we're going to make that coefficient to be 1, and so this implies that, of course, we're assuming here that the mass is a positive number, in fact not equal to 0, so dividing by the mass is totally fine. So this becomes something that looks like this: x double prime time plus a constant times x equals 0. And this is what we're familiar with, this type of second order homogeneous equation, right? So here we would say, let x be of the type e to the rt. That leads to x double prime leads to the following characteristic equation. This becomes r squared plus k over m equals 0. So we go from second order equation into finding the roots. Now we'd like to solve this characteristic equation, solve this for r, right? So, and then this leads to r squared minus k over m, and therefore r being plus minus I times square root of k over m. So now you can see the motivation. We can consider this square root with a new name. So we're going to rewrite this as plus minus I omega sub 0. So in other words, the roots of that characteristic equation are plus minus I omega 0. And then this would imply that complementary solution is of the type C1 E. Well, the other thing to realize here, if I may, is that this, hold on a second. So let's say, in other words, R can be expressed as 0 plus minus I omega 0. Okay, so let's keep that in mind, because now we're going to write x sub z of t, c for complementary, as something that has the form c1 e to 0 t cosine plus c2 e to 0 t sine right? And so this would be the part where we write this in the form, say, t omega 0 as the argument, t omega 0. You can also write omega 0 t as the argument of these trigonometric functions. So we were able to then derive here form, maybe I can write this in an extra line, so we can write x sub c of t, something that looks like c1 cosine omega 0 t plus c2 sine omega 0 t. We'll come back to this, but now let's work on a particular solution. For a particular solution, we're going to consider the following problem. Okay, so notice that what we're writing here, this is the forcing function, right? Here, this is the idea of the force is with you. That's why we write here that that's the action of that force on the that force is this force that's pulling the object of mass t, right? The argument of this forcing function, sometimes you call this seasonal forcing because the cosine function is a well-known periodic function or seasonal function, right? Seasonal forcing sometimes is called. So this argument here is omega, and not the same as the omega 0, but notation looks very similar. So we're going to say, look, if omega 0 is not omega, and this is not just notation. Remember, what was omega 0? We had made a comment here about what this was. Omega 0, the so-called natural frequency. It's that frequency, you know, that's kind of pulling the system to oscillate, to kind of dance the dance of that oscillation, a specific tune, right? That omega 0 is denoting the natural frequency, different from this other frequency, if you will. In general, we assume they are different, then propose a solution to be xp, this meaning xp of t, of the form a cosine plus b sine. What are the arguments of these periodic functions cosine and sine? Why? Well, we'll get to that. So where these arguments are omega t, omega t. They're not omega 0, they're omega t, omega t. But if this is what we're proposing, okay, so let's work with this. So this is what we're proposing, that is xp. So this would imply that first derivative of xp, first derivative of x prime, is something that looks like minus a. Here you have to remember that this requires using the chain rule, right? So chain rule all the way chain rule. So that chain rule is going to cause an omega, constant omega, to appear here, and then we will write derivative cosine. Of course, this would be sine, and then omega t. And consistently, we'll write here b times omega times cosine of omega t. That would be the first derivative. Okay, so let's now work with differentiating this yet one more time. So this would imply that the derivative of the first derivative is the second derivative. That's also going to bring another of these terms. When we apply the chain rule, the derivative of omega t with respect to t is going to be omega. That's going to bring another coefficient of omega, and this is going to make this expression look like this: minus a omega squared cosine of omega t. And here, again, by action of chain rule, we're going to get an omega, and then there will be a negative due to the derivative of cosine. So this would look like minus b omega times omega omega squared sine of omega t. You will see where I'm going with this, but eventually we're going to need to actually multiply this expression by m. So let me write this in one more line as m times x double prime p that means we have coefficient m there. Everything else kind of the same. So this is minus m a omega squared cosine. Then there will be another m here. So this is minus m b omega squared sine omega t. And this is cosine of omega t. You'll see why I wrote this in a minute, so that comes an implication from the previous line. Also, if we multiply x, the solution, the particular solution, by k times xp, okay, if we multiply the particular solution here by k, we're going to have ka cosine plus, looks like this, ka cosine plus kb sine. So let's now consider an evaluation of this. You know, sometimes we refer to this as an operator. So this second order equation, m times the second derivative plus k times the actual function. So next, that means that if we consider m x double prime p plus k x prime, it's basically adding up, it's basically bringing together these, adding these, all these terms, adding them together, right? So if we do that, we would be able to collect terms, right? So you can picture here the terms that have cosine. So we can write something like, okay, let's write here cosine as a common factor. This will be cosine as a common factor, and then that would include minus m a omega squared, and then plus k a. That would be what multiplies cosine. And then we can do something similar for collecting the terms that have the sine function there. So plus this here times sine right? And so the terms with the sine function will also include something that looks like minus m b omega squared plus k b. Of course, the argument of cosine and sine is omega t, omega t. So what comes next is, this is basically, want you to keep in mind something here. So this would be considered the left hand side of this equation, and then here this would be the right hand side. So the work we've done before is by using the particular solution. So that means that the left hand side, the equation when solved, is something that looks like this, right? It looks, maybe I rewrite it as Ka minus ma omega squared plus kb minus mb omega squared. So this is, the first one is multiplying cosine, second one is multiplying sine, right? It's just, I'm just rewriting exactly what we have there. But this is simply taking care of the left-hand side of that differential equation. The right-hand side, okay, the right-hand side has an expression that looks like this. It looks like f0 cosine. And in fact, I'm going to add an extra term there. Doesn't hurt, a 0 times sine, because you should look at this with malicious intent, and that malicious intent would be that you want the left-hand side of the equation to be equal to the right-hand side, and you can right away see that certainly there's an expression here with cosine that you're going to say, yeah, this is going to work with this one that has cosine. And then there is also an expression here that has sine, and you want to be able to equate that to something. So this is a sign that has all the arguments of the trigonometric functions are omega t. So now, because of, by comparing or by equating left-hand side equal to right-hand side, right, this is true if and only if the coefficients of these functions are equated to each other. In other words, this is going to give us the comparison of say Ka, so we're comparing this coefficient minus ma omega squared. That will be compared to the coefficient of the cosine at the right hand side, which is here denoted as a constant f0. Also, we would compare coefficient of sine, which would be kb minus mb omega squared. Would compare that to, see, this part here, we compare that to 0. So I'm going to call these expressions, maybe give them a name so we can refer to them. So here's equation 1, and then here is going to be equation 2. So let me work with equation 2 first. So let's manipulate. So from 2, it follows that we can have, we're going to factor b. B is a common factor there, so we can write this as b times k minus m omega squared. This is equal to 0. So either b is equal to 0, so either b is equal to 0, or k minus m omega squared is equal to 0. So one of those two things would have to happen. Also, equation 1 here would imply the following. Is this expression, right? And then we can work the left-hand side, a multiplying k minus m omega squared, this being equal to f sub 0. Which implies, or if and only if, here a is f sub 0 over k minus m omega squared. Okay, so let's remember that since we had a definition of the natural frequency. The natural frequency is the square root of k divided by m, right? So if we were going to square this on both sides, then we would obtain that that natural frequency, the square of the natural frequency, is the ratio k divided by m. And in fact, we could represent here k as m times omega squared. This would be equal to k. So these statements are if and only if k can be expressed as m times omega 0 squared, not the same as omega. K is times the natural frequency, is the square of the natural frequency. And so that means that we can go back to this expression and substitute and find a new expression. So we rewrite A, meaning that now we can write A equals F0 over m omega 0 squared. Maybe I should write that with a different color, shouldn't I? Just to be more colorful, okay? So we write k as m omega 0 squared minus m times omega 0, minus m times omega squared. And so then this would kind of in a more compact form, the denominator could be expressed as m times quantity omega 0 squared minus omega 0. Okay, so this means we've found that the big thing was these coefficients, a and b. Okay, coefficients, there is an expression for coefficient a, and here there is another expression for, there is here an expression for coefficient b equals 0, and here an expression for coefficient a in terms of f0 and yeah, I have a little typo here. Sorry. This denominator, let me rewrite that denominator, okay? This denominator is simply, nothing has changed. This is omega squared. So this would be omega 0 squared minus omega squared. The only thing that we did with that denominator was to write m, the mass of the object, as a common factor, okay? So, but these coefficients a and b, they go back to where they come from? Well, they're coming from because we propose a solution, okay? We propose a solution that has coefficients a and b. This is a solution that's a linear combination of cosine and sine with coefficients a and b. So now we can say, you know what, after all this work, we have found what xp, we can write x sub p. Therefore, we can write that x sub p, this will be x sub p of t, is equal to, remember, this is a cosine plus b sine, but it doesn't matter what is the argument there because this b coefficient is 0, so we can really write x, the particular solution xp, as a times cosine, and this a is something that we can express as f0 over m times quantity omega 0 squared minus omega squared. So the argument of this cosine here is omega t. So in this form, we can now write a general solution. We can now write a general solution, which is an addition or a sum of the complementary solution and the particular solution. So we propose the general solution x to be of the form x sub c plus x sub p, right? So more generally, x of t is x sub c of t plus x sub p of t. So that means x of t, something that looks, maybe I should write this complementary solution here. So of the form c1 cosine plus c2 sine plus the particular solution, which is of the form found as f0 over m times quantity, and that fraction multiplies cosine. Now the arguments here, the first part for the complementary solution, these arguments are omega 0t, omega 0t. Remember, this omega 0 is the natural frequency. And the argument for the cosine function, the particular solution, is omega t. So I need to write something here, which is omega 0 square minus omega square. Now, there are three functions involved in this general solution, and I could rewrite these two functions. So this is a sum of three functions. I could rewrite these two functions as c3 cosine of something, and this is still adding f0 over m times quantity, and this multiplies cosine, right? So the argument of this cosine would be omega 0 t minus gamma, and this argument continues to be omega t over here. And so this denominator is still omega 0 square minus omega square. So this is now the general solution. Okay, this is now the general solution of this problem, which is formally known as undamped force motion, right? So the damping coefficient is 0. This is still a second order equation that is equated to some type of forcing in terms of the cosine function. And then we have found that the general solution of this equation is still expressed as a function. It's basically a linear combination of cosine functions, but an important part here is how to rewrite this linear combination of cosine and sine as just one. So you can see the action here of one of those formulas for the addition of angles as arguments of the cosine function.